So I'm Jessica Laughlin. I come from a software engineering background. So I was previously an engineer at Goldman Sachs, at Bluecore, which is a marketing tech startup. And I was an early engineering hire at Materialize. I've been at Materialize for a little over 5 years now, and I'm currently Materialize's head of product. So I've spent some amount of time thinking about what makes a streaming system good. Now, it's pretty rare to get to stand in front of a room of folks spinning up and using streaming systems in production. I'm going to risk it and ask you all, what are some qualities or characteristics that you look for when you choose a streaming system? You can shout out.
Reliable delivery.
Yeah, reliable delivery for sure. Anything else?
Easy to operate.
Easy to operate, yes, definitely.
Low latency.
Low latency, yeah, a key one. Throughput. Hey, Josh. Yeah, so I have a simplified answer here, and I wrote down when it lets you act quickly and autonomously on the outputs of your changing data. Because stream processors generally unlock two things. You can suddenly move very, very quickly on your changing data, and you can do that autonomously because you can trigger some actions automatically rather than requiring some human input or otherwise manual intervention. Now, this is a simplified answer, but it's actually not a simple one, because as you all mentioned, it takes a lot to get to this. So you need a system that's low latency, you need a system that's high throughput, that's scalable and can meet the requirements of your workload and data spikes, and you need a system that's fault tolerant, so something that won't lose data in case of failure or lose processing integrity. And you might care about other things like deployment model, ease of use. But today I'm going to argue that there's actually another piece of the equation that we should be thinking about when we're choosing stream processors for our production workloads. And we don't just want to move quickly and autonomously in all cases. We want to move quickly and autonomously on the correct outputs of your changing data. To motivate this, I'm actually going to be working through an example for the rest of the talk. So I'd like to introduce you all to Payco and hand-drawn diagrams that you'll be seeing for the next 30 minutes. So Payco is a hot new fintech startup that makes lines of credit and credit cards available to its users. And these users go out into the world, spend money, pay Payco back on some schedule. And everything's great until one of these purchases isn't authorized. So imagine user 3 here unfortunately fell for one of the cheesy phishing attack emails. They clicked a link, and now somebody has their credit card information, and they're making purchases on their Payco card. When customers spend with their Payco credit cards, they have to pay Payco back. But when fraudsters spend money using the Payco credit cards, Payco's liable for those transactions. They couldn't reasonably ask customers to pay them back for fraudulent spend. No customer would agree to that, and it's generally illegal. So Payco is heavily incentivized to identify fraud and stop it quickly. But Payco needs to make that call to approve or deny a transaction pretty quickly, probably within a number of milliseconds, if you think about swiping your credit card when you're buying coffee or an online purchase. So you might think they want to use a stream processor to detect and prevent fraud. Because as we touched on earlier, stream processors allow you to move quickly and build applications that act autonomously on your changing data. Payco certainly needs to move quickly as new transaction data, behavioral data, merchant data arrives. And they need to act autonomously, otherwise they wouldn't be able to return that not fraud determination within milliseconds. But unfortunately, most stream processors don't guarantee that you will be acting on correct outputs at any point in time. Now, for some folks, this idea may be new. So in what circumstances might your stream processor return incorrect results? To understand how and why, let's dig into consistency. Confusingly, consistency can mean different things in different computer science contexts. So I'll explain what I mean through a pretty simple example. So systems have some logical state which changes over time, and operations transition from state to state. And when there's a single operation at a time, it's pretty clear what should happen. So in this instance, X should be updated to 4. But when there are multiple operations that take place concurrently, things can get a little less clear. So imagine you have one operation that's trying to update X to 4 and another that's trying to update X to 2, and they arrive, sort of concurrently. operations themselves take some amount of time. So if you're looking at this, it might not be obvious when you read from it if you're going to get the value 4 or 2 back or 3. As you add additional operations, the exact state of a system at a given point in time gets less clear. So it's obvious that we need to define some rules that tell us, the users, what we can expect from our systems when we interact with them. To formalize these expectations, we create consistency models. So consistency models tell us about the behavior of a system and describe the guarantees that we get from it. So it will tell us the legal outputs of a system. And that over there is what we generally think of as consistency. So as operations change the state of our system, we want to be sure that those operations only bring the system from one valid or legal state to another. But you'll notice that I'm not spelling out exactly what legal or valid is here. And that's because there are varying levels of consistency guarantees that you can get from your data systems, or that you might want to choose for a given application or use case. In the databases and distributed systems world, folks have spent a lot of time thinking about defining and improving the consistency guarantees of their systems. Consistency models that are more permissive allow a wider set of valid outcomes at any given moment in time. They're typically referred to as weaker. The weaker guarantees can be found at the bottom of the diagram, so the read uncommitted, the writes follow reads. And these weaker guarantees are often optimized or chosen for performance or availability, which we'll touch on a bit at the end, at the expense of tolerating data anomalies. So to give an example, read uncommitted here introduces a few different data anomalies, one of which is dirty reads. So dirty reads can show the user data from an ongoing transaction that has not yet been committed. In the case that that transaction fails or is rolled back, the user will have read and potentially acted on data that was actually never valid in the system at all. As you move up the diagram, the consistency models get more restrictive. One moment, it's a lot of talking. The consistency models get more restrictive. So these models eliminate different classes of data anomalies, allowing it for a smaller set of valid inputs at any moment in time. Because of this, these consistency guarantees up top are referred to as stronger. So for example, serializable, up there on the top and the left, ensures that the outcome of concurrent transactions, like X updating to 4 and X updating to 2, that the output is equivalent to some sequential execution of those transactions. And strict serializable, all the way up here at the top, probably describes what we all intuitively want from our data systems. Strict serializable guarantees that operations not only appear to be executed in some sequential order, like serializable, but that they reflect real-time time constraints, so what you'd observe in the real world if you were collecting that data. But as I mentioned earlier, most stream processors can't guarantee that they will be giving you correct results at any given point in time. That's because in the world of streaming, unlike the world of databases and distributed systems, most systems only guarantee eventual consistency. Now, eventual consistency only tells us, the user, that if the input stops changing, the output will eventually converge to the correct result. The modifier in eventually is intentionally vague here. An eventually consistent streaming system can fail to produce correct results for milliseconds, seconds, minutes, hours, and technically, by its definition, indefinitely. So some of you may have already worked with distributed key value stores that have eventual consistency guarantees, so you might be thinking, this is nothing new. But unfortunately, your intuitions from those systems don't always translate well to streaming systems, particularly when your computations get more complex. Where eventually consistent key value databases might show you stale results, eventually consistent streaming systems might show you outputs that are completely impossible for any set of inputs. And the system might never converge to a correct result as long as your inputs keep arriving, which they typically do in streaming systems. To illustrate, let's explore how you can read incomplete, incorrect, or even no data at all from your streaming system. So what does it mean to read incomplete data? Intuitively, this is what happens when you read a stale value from your eventually consistent key value data store. It's the same here. So let's imagine that Payco created this pretty simple query to detect fraud as one of their flags, and they're just looking at how many transactions a user has purchased in the last hour, and a high number of transactions looks questionable. It's possible that your stream processor is keeping up with your stream of transactions and that the count here is up to date. But it's also possible that your stream processor is falling behind and showing you a stale count. That's because the input stream transactions, until it stops changing, most systems won't guarantee that you'll get a correct result here. So in our example, that means as the fraudster starts to rack up purchases, keeping that transaction stream flowing, Payco might find themselves deep in debt before the count here reflects a worrying and up-to-date count. Now, once again, I'm standing in front of a room of folks who have built, spun up, and operated streaming systems in production. So some of you might be thinking, simple queries that are just reading or selecting from a stream, probably as simple as transactions, should produce output pretty quickly. And while that might be true in practice, my point in this talk is that you're not guaranteed that. There's nothing about eventually consistent systems that assures you that you will be reading the correct output at any particular moment in time unless that input changes, or while that input is changing. But if you're not worried about this simpler example, let's make it a little bit more complex. So imagine that Payco notices that just counting the number of transactions in the last hour isn't actually a great fraud detector. They want to beef it up by if the user has a high transaction count and the merchant is currently untrusted, so something about the merchant has gone wrong. And this will give us an example of how you can read incorrect data from your stream processor. Because this query is now reading from 3 streams: transactions, users, and merchants. And speaking generally, eventually consistent systems are badly suited to the problem of aligning data. They aren't able to synchronize multiple streams when they join across them. So when you're reading from a query like this, you might be reading one moment from your transaction stream, another moment from your user stream, and another moment from your merchant stream. You're probably wanting to get a result that reflects some moment in the real world, but you're not guaranteed that. So if there is a real world moment where the transaction count is high and the merchant status is untrusted, you're actually not guaranteed to catch that with an eventually consistent system. But you might be thinking, in practice, my stream processors keep up with my data. Do I really need to worry about this? I borrowed this from Jamie Brandon. His blog is linked here. The blog is good. I'd recommend you read it, but I'll tell you about it. So Jamie Brandon explored the eventual consistency guarantees of some popular streaming systems with the following use case. So he created a stream of 10 million transactions moving money between 10 distinct accounts. The amount of money moved was always $1, so you could eyeball the scale of errors here. The transactions generated had 60 distinct timestamps that could be out of order for up to 10 seconds, simulating a common CDC stream. But most importantly, money was never created or destroyed. It was just moved between accounts, so the sum here should have always been 0 across all accounts. So we've been talking about how eventually consistent systems can't guarantee to produce the correct output until their input streams stop changing, and your intermediate results here can be incorrect. During his testing, Jamie found that many popular stream processors can return wildly inconsistent intermediate results up to and breaking application invariance. And unfortunately, he found that these results were easier to trigger than he would have guessed. In his post, Jamie explains that stream processors were originally used for high temporal locality use cases, or those use cases where same or related data points typically occur within a short time frame, like analytics. These original use cases could tolerate some bounded amount of error because their consumers didn't care or typically wouldn't notice. But as folks have started building more and more of their applications directly on top of stream processors to unlock acting quickly and autonomously, they've started to build low temporal locality use cases on them as well. These use cases include operations like unwindowed joins or long-running aggregations. These use cases and calculations don't have a natural endpoint in the same way that high temporal locality use cases do. So these types of intermediate inconsistencies that you may see from an eventually consistent streaming system are now able to cause larger and more ongoing problems. At this point, you might believe me that eventual consistency can show you stale data, it can show you incorrect data, but I also said no data at all. If streaming systems do anything, they're moving through a lot of data and fast. How is that possible? To illustrate, imagine Payco wants to know the maximum amount of money that someone has spent on a given category, so they can identify that category for a much larger fraud query. A reasonable person would expect to get the max category back from this query. But now that we know some of the problems with eventually consistent streaming systems, we might walk back our expectations and say, we'll get some category back. It might not be the max at the time we read it, but we'll get some category back. Unfortunately not, as long as the inputs are allowed to change. Imagine the join here between transactions T1 and select max T2 amount from transactions T2, that join. Imagine it receives its inputs consistently later for transactions T1 than for the select max T2 amount from transactions T2. This isn't unreasonable, as it can be easier to maintain a max than it is to maintain a whole collection. If each newly arriving transaction increases the maximum spend, the transaction side of the join, T1, won't have that information yet. So it'll be looking for a record that doesn't exist and will return no data at all. And if you get caught in a pattern where potentially the output keeps changing and you're trying to join against it for some period of time, you're going to be returning no data. So all that to say, eventual consistency doesn't tell us, the users, very much about what they can expect from a streaming system. It tells us that we can expect the correct output eventually, but until the system converges, we don't get many guarantees about those intermediate states, their legality, how valid they are. The outputs you're reading can be stale, incorrect, or you can get no data at all. And that's the major pain point for building applications on top of eventually consistent streaming system. Who even really knows? If you're acting on the output of your system at any given moment in time, it could be wrong, and it could be wrong often. So let's say you want to wait for it to be correct. How long do you wait? If you want to flag a transaction as fraud, shut down a line in manufacturing plant, or send an important push notification to a user, how would you do that? How much time would you have to build into your low latency system to account for that transient wrongness? But you might be thinking, that's fine. Most stream processors provide some sort of exactly once guarantee. And often when you look up the consistency guarantees or the correctness guarantees of a streaming system, you are rerouted to a discussion on their exactly once semantics. So surely something about their exactly once guarantees should ensure that we're acting on correct data, right? Again, unfortunately, not. So exactly once is not a consistency guarantee. It's just a processing guarantee. So for a result generated by a stream processor to make sense, it must do two things. First, it must reflect the inputs that were ingested into the system. And second, it must do so in a way that is coherent with the time at which those events were generated. Many stream processors have only focused on the first half of that equation. So exactly once guarantees ensure that every input processed by the system is accounted for in the output, which is definitely important, because you can be assured that no message is lost or duplicated, even in the event of failure. But exactly once message processing doesn't do anything to ensure the second part. So it doesn't do anything to ensure that the outputs of the system are shown in a way that is coherent with time. So let's bring this all back to our friends at Payco. They want to move quickly to determine if a transaction is fraudulent or not, but they also want to make that call correctly, because there are real costs to getting the call wrong in either direction. If they deny a real transaction, imagine you're a Payco customer and some, non-0% of the time they're flagging when you purchase a coffee. You're eventually going to use your Payco card less and potentially churn altogether. But you also don't want to approve fraudulent transactions because Payco's on the hook for those. So they need a system that provides the traditional hallmarks of streaming systems, the one we talked about all the way at the beginning of the talk, so low latency, high throughput, scalability. But they also need a system that makes stricter guarantees about the behaviors and outputs of the system, particularly as the inputs keep arriving. The good news is that there are streaming systems that combine the superpowers of stream processing with the stricter consistency guarantees you'd find in the world of databases. So to highlight this, I'm going to focus on two streams or systems in particular, the ones that I know best, Materialize and differential data flow. So Materialize is an operational data store built to let users and services act quickly, autonomously, confidently on their changing data, just using SQL. So Materialize ingests data from upstream systems like Postgres, MySQL, and Kafka, and then lets users transform that data through indexes and Materialize views. Materialize incrementally maintains the results of user queries by compiling their SQL down into differential data flows. So differential data flow is a framework for efficiently performing computations on large amounts of data and maintaining those computations as the data change. And a neat thing about differential data flow is it's consistency preserving. So consistency preserving means that differential data flow is able to offer consistency guarantees as strict as the upstream systems that it is ingesting data from. So Materialize, with differential data flow as its compute engine, is able to offer a range of consistency guarantees to its users. So when users ingest from eventually consistent sources, Materialize is only able to offer eventual consistency. But when users ingest from sources that offer stricter consistency guarantees, Materialize is able to offer those same guarantees over their streaming changing data. So when users ingest data from a system like Postgres, for example, Materialize is able to offer strict serializable guarantees, the guarantee we talked about earlier, all the way up there. How exactly can Materialize using differential data flow do this? Materialize employs a technique called virtual time, borrowed from the distributed systems world, which says that events should be timestamped prescriptively rather than descriptively. The recorded time says when an event should happen rather than when it did happen. This means that as Materialize records, transforms, and reports continually evolving, explicitly timestamped histories of collections of data. And these explicit histories unambiguously communicate the exact contents of a collection at any given moment in time. So if we get back to our simplified consistency example from earlier, the virtual times here are represented by T0, T1, T2. If a user wants to read from Materialize at T0, they'll get the value of X is 3, T1, 4, T2, and beyond 2. To understand how this works, let's take a brief and high-level overview or tour through Materialize's architecture. So Materialize has a storage layer that connects to and then continually ingests from upstream systems. And as it ingests data from a variety of upstream source types, the storage layer is tasked with assigning virtual time to each update, which becomes the truth about when that update happened. So the assigned times must reflect the constraints from the upstream system. So updates in the same input transaction must be given the same virtual time, or updates that are ordered in the input must be given virtual times that respect that order. Ideally, Materialize would assign timestamps to updates that track the exact moment of change in the upstream system. Some upstream sources are sufficiently specific about their changes. So for example, Postgres moves forward with the log sequence number, the LSN up here. Other sources of data aren't as specific about their changes, and Materialize instead reclocks their sequence of states into its own virtual time. So Kafka, for example, a tool you are likely all familiar with, is a little bit more complicated. So each topic is comprised of a number of partitions, each of which moves through integer offsets. So rather than a single log sequence number, or LSN for Postgres, each time has an association between partition IDs and offsets, including a 0 for partitions that have not yet come into existence. Okay, but regardless of the upstream source type, once recorded, the explicitly timestamped history of the ingested data is unambiguous on matters of concurrency. So then the compute layer is tasked with efficiently computing and maintaining the views over those explicitly timestamped histories of data. When a user creates an index or a materialized view in Materialize, we compile that SQL down into a differential data flow. Differential data flow is a high-performance, scale-out data flow system designed exactly for the task of maintaining consistent views over changing data with high throughput and low latency. The data flows then incrementally maintain the results of the user's queries as new data arrives, outputting histories that correspond to the exact input histories. Last but not least, the adapter layer is tasked with assigning timestamps to user actions to present the experience of a system that moves forward sequentially through time. So to do that, the adapter layer assigns a virtual timestamp to each user command. And once this has been done, the operation of the rest of the system has been determined. So Materialize has some work left to do to actually return the result to the user, but the coordination problem has been reduced to producing the correct answer for a particular virtual time. So when Materialize is doing its job well, the most recently assigned virtual timestamp is pretty close to right now, and you just need to wait a moment for correct, up-to-date results. So let's return to the examples from earlier that may have struggled with eventually consistent guarantees. The select count star here would always be up to date in strict serializable mode and always reflect every transaction that that Materialize has ingested. So each time you read from this query, you'd get the correct up-to-date count of the transaction stream. And you'd never miss a moment where a user's high transaction count intersected with an untrusted merchant status. Because Materialize creates and maintains explicitly timestamped histories collections of data, when it joins across multiple streams, unlike eventually consistent streaming systems, it's able to use those timestamps to synchronize its joins. So instead of getting potentially 3 different moments between transactions, users, and merchants, you're looking at the same moment, so a real-life event that would have happened in the real world. And for the same reason, for the timestamp synchronization, you'd always get the category with the user's max spend back here. So when Jamie, our friend who wrote the blog post, tested differential data flow, Materialize's compute engine, unlike the eventually consistent streaming systems, he found that differential always maintained a sum of 0 at all times. No money was created or destroyed, and the user never saw an incorrect intermediate result. For Payco's fraud case, they'll need a streaming system like that. They need to act quickly and autonomously, but they need to ensure that they're acting on correct data at any given point in time, and stricter consistency guarantees can give them that confidence. They can be assured that they will not act on a false flag in either direction. So the talk could have ended here. I did solve Payco's problem. I told you all about stricter consistency guarantees. But wait, there's more. What if you need even stricter consistency guarantees? What if you're not satisfied? What we've been talking about so far, you can think of as internal consistency. So the consistency guarantees that a system gives once data is ingested into it, so that every output is the correct output for some subset of its inputs. But what if your use case needs consistency guarantees across multiple systems? At Materialize, I've actually worked with customers who want their reads from their stream processor to reflect their most up-to-date and recent data in their upstream source of data as well. So in our fraud case, imagine that Payco is writing all their transactions to some OLTP system, and each time they read from their stream processor, they want to be sure that its outputs reflect all of the new inputs into their OLTP system. So it is possible for streaming systems to support this type of guarantee as well, and it's called real-time recency. So in Materialize, implementing real-time recency means that not only can we provide strict consistency guarantees over the user's streaming data once it's ingested into Materialize, we can guarantee that the user's reads are actually synchronized with their upstream system's writes. So you'll remember that Materialize assigns virtual timestamps to user actions. That includes select statements. So when Materialize is set to real-time recency, we'll assign a virtual timestamp to the read, and we'll ensure that the read reflects the inputs at that time in the upstream system as well. And with real-time recency enabled, Materialize can be faster to calculate and return results of complex analytical queries than performing them directly on your primary database. Materialize computes and then incrementally maintains query results thanks to differential data flow, our compute engine. And it does not have to wait out replication lag and only then start processing your query. So Materialize can start processing your query immediately with the data it does have and update the results as the necessary bits of your replication log stream in. So when user queries arrive, much of the work to answer the user's query is actually already done, and it's often just a matter of waiting out the last bit of replication lag. That means that Materialize can let you act more quickly on the outputs of your changing data, sometimes than even working on your primary database itself. Because while the primary has no replication lag, the response time of OLTP systems, particularly for complex analytical queries, isn't always that great. And although Materialize has some replication lag, its response time can be better. While the primary is still working on the query, Materialize has already incrementally updated and returned results. So we've talked about a few different levels of consistency in this talk: eventual consistency, serializability, strict serializability, real-time recency. My goal here was to highlight what is promised and notably what's not promised by weaker consistency guarantees, and share that stricter consistency guarantees are available in the streaming world. But we haven't spent too much time here thinking about the trade-offs of opting into stricter consistency guarantees. And as a room of folks building technical products, we all know there's no free lunch. So this is the same consistency diagram that I've been sharing from Jepson or Kyle Kingsbury, but it includes the key. And you'll notice that each of the consistency models here are labeled in terms of the availability you will have or you might give up as you pursue that level of consistency. So weaker guarantees can't ensure that you're acting on the correct outputs at any given point in time. But when you give up on correctness, your system will generally be more available and return results faster. And as your consistency results get stricter, you're going to pay in terms of availability and occasionally performance. In Materialize's case, we actually default to strict serializable isolation for our users and their applications. But some of our users downgrade to serializable if they want to make that trade-off between correctness and latency. The good news about serializable, as opposed to eventual consistency, is it is always a correct output. It just might not be the most up-to-date output. So you're still eliminating that moment where you might be acting on incorrect intermediate results. But potentially you have a use case where availability and performance is even more important than that. The consistency level you choose is a trade-off between correctness and availability and will be specific to your specific use case and application. So at the beginning of the talk, I said that typically we consider a stream processor to be good when it lets you act quickly and autonomously on the outputs of your changing data. But as we continue to move more applications and more use cases to be powered by our stream processors, we should at least consider if we need to be acting on the correct outputs of our changing data too. In my experience, many stream processors don't make their guarantees about consistency or correctness very clear or readily available to its users. So they don't spell out the anomalies that you can run into, how often, what they might look like. So if you take away one thing from my talk, I hope it's a prompt to evaluate the guarantees of your streaming system if you don't know them already. Because you may be fine working with eventually consistent guarantees, particularly in like those high temporal locality use cases or where availability and latency is much more important. But if you're watching this talk and you're thinking, I have maybe one of those low temporal locality use cases. I have unwindowed joins. I have long-running aggregations. You might want to consider if you need a different tool for that job, even if it's just for one use case. Because there are some use cases that are too important to act on incorrect data, whether it's detecting and preventing fraud or writing the title for your talk. Thank you all so much for spending the time here today.